So in this video we are looking at cryptography again, but this time we're comparing the difference between symmetric and asymmetric encryption, talking about some of the issues and giving you some examples of this type of encryption, or both types of encryption. So with symmetric encryption, which is like your Caesar cipher, pretty much the usual situation is that Benedetta's maybe got a message that she wants to send to Alvise, and Alvise knows the secret key that Benedetta is using to encrypt it. So Benedetta shares that with Alvise. Alvise knows the secret key, and then when he gets the message, he can decrypt it and work out what it's meant. Symmetric encryption, all types of symmetric encryption, work on the principle of a shared key. So by that I mean that the same key is used for both encryption and decryption. So this worked fine up until maybe the mid-1990s, and then asymmetric encryption came along. And this is the idea of public keys. So Benedetta and Alvise, Benedetta is still sending her message, and she encrypts it and sends it to Alvise, but to stop people from working out the secret key. And so Benedetta knows her private key, but she shares her public key with Alvise. Benedetta has already sent a message, and Alvise wants to send a response. So here's his response, just in plain text. He can use Benedetta's private key to encrypt his own message and then send it across to Benedetta. Benedetta can then decrypt that message using her private key. This is really secure compared to the symmetric encryption. Two reasons. One, the public key is open and accessible to everyone. It's sent, unencrypted across the internet. Anyone can look at that, anyone can read it, anyone can use it to make a message for Benedetta and send it back to her. But because Benedetta never shares the private key, it remains on her computer and only known to her. She is the only one who can decrypt the messages that are sent to her, which have been encrypted with her public key. So one of the problems of asymmetric encryption is that it is open to something known as a man-in-the-middle attack. This is where someone can intercept the communication between Benedetta and Alvise. But not only that, they can impersonate that person by intercepting their transmission of their public key, changing it to their own public key, and passing it on to the recipient, while pretending to be the original sender. If there's no verification of the sender's identity, then there is no reason why the recipient should believe that it's a man in the middle, and so they can encrypt their message using the key, the public key that they think belongs to the sender, and pass it back. But of course the man in the middle can intercept that again to decrypt it using their own private key, and so then they can read the information. Now, as well as being able to read the information, they could potentially change the information, and if they can change the information and then pass it back, Benedetta will receive something which looks like it's come from Alvise, but it maybe has been changed by the man in the middle. Okay, this is an example of a man-in-the-middle attack. With our previous discussions about asymmetric encryption, you know that Benedetta has to send her public key to Alvise before Alvise can send his message back to Benedetta. Now, this is how it works. So, Benedetta sends her public key along the network. The man in the middle manages to intercept this, change it, forward it on to Alvise. Now, Alvise thinks that the public key he's just received has come from Benedetta, so he just simply uses this to encrypt his message with the man-in-the-middle's public key. It sends it back to Benedetta. Again, it is intercepted by the man-in-the-middle, and because the message was encrypted with his public key, he can decrypt this using his own private key. You can read what the message says. Here's an example. Benedetta is going to pay Alvise some money through PayPal. Alvise sends his PayPal account email address. The man-in-the-middle attack decrypts this, works out that it has something to do with PayPal, changes it for his own PayPal account, and then sends on the changed information back to Benedetta. Now, remember earlier that Benedetta sent her public key originally, and the man-in-the-middle managed to obtain it. So once he's decrypted and possibly changed the message, he can re-encrypt the message using Benedetta's public key, sending it back to her, and she is none the wiser. Now, there is a way to get rid of the man-in-the-middle attack, very, very simply, and that is to authenticate the person who is sending the message and receiving the message. And you can do this through something known as digital certificates. So a digital certificate is a way of identifying somebody as being who they say they are. It's a bit like a passport for each computer system. So when the communication is initiated, a certificate is sent saying who the person is. But then the certificate is verified using a third-party service. And because of this, someone attempts a man-in-the-middle attack. The message, before it's decrypted, the certificate is checked, and if it is not from who it claims to be, then the message is deemed as insecure. So if you think of digital certificates, they verify the identity of an individual computer on a network. But there's other forms of identification and verification. One is a humble barcode. If the barcode doesn't scan in a supermarket, for example, the checkout person can usually type in the code and it finds the item in the supermarket database. But to make sure that these numbers or lines aren't interfered with in any way, barcodes have what is known as a check digit at the end. And this check digit is calculated through use of an algorithm, and that algorithm changes depending on the type of barcode which are used. Anything that has a long series of numbers will probably have a check digit at the end to make sure that so the digits aren't entered incorrectly. So for example, if you try and scan a barcode and it doesn't scan, so you resort to typing in the barcode number, but you accidentally type in the wrong barcode. If there's not a check digit there, you might accidentally end up charging the customer for a bottle of champagne when they've bought a bag of pasta. This could seriously affect the profit margins of the company you work for. So a check digit is useful to remove the chance of human error. Checksums are used to avoid the transposing of digits. There's also other methods of checking validity of data, things like checksums. This mainly applies to network traffic, so we'll look at that later in the course. Let's go back to the idea of cracking passwords. Crack an iPhone PIN code, for example. Now, it didn't do the cracking, but it generated all possibilities, and we called that brute force. And while the program itself took a long time to create, actually running the program, once you've built it, doesn't really take that long. And this is a problem because with symmetric and asymmetric encryption, if you have a secret key or a public key that is an insufficient length, then brute force methods can be used to crack it. This is why the current encryption standards are up to 256 bits. So you've got AES 256, and that uses 256 bits to encrypt and decrypt the messages. Why does it have to be that long? Each of those digits stored in ASCII would be 8 bits, 32 bits. If we try to work out how long it would take to crack a 32-bit code, the CPU of a Raspberry Pi, for example, runs at the speed of 24 gigaflops, and that means that it can do 24 times 1024 times 1024 floating point operations per second. If we multiply that by the number of seconds in a year, the number of combinations in 32 bits is 2 to the power of 32, and that gives us a total number of combinations. And so if we take the total number of keys that can be generated per year and divide the total number of possible combinations by the number of keys per year, you get 5.67 years roughly to generate all possible key combinations. Given that most brute force hacking methods will find the key at about halfway through the possible combinations, you're looking at maybe just half of that or just over half of that. So maybe 2 3/4 years with one computer, one Raspberry Pi, to crack all possible combinations of 32-bit keys. Now, our initial challenge, which was to generate the codes between 0000 and 9999. So if you know a little bit more about the code that you're trying to crack, you can actually reduce this number here, which obviously reduces the time taken here. So instead of taking 5.67 years, it now takes, for 10,000 possible combinations, just 6.9 minutes with the same computer to generate all possible combinations. So it's essential that the programmer who's implementing encryption uses a suitable amount of bits. And please just remember that that is just the value for one computer. If you use a number of computers, you can reduce the time that it takes to brute force all possible combinations by a significant factor. Other techniques that can be used to discover the secret key used in communications. A number of hackers or crackers use something known as a ciphertext only attack, where the hackers or a group of hackers build up over time a collection of encrypted messages between two parties. Eventually, you begin to recognize patterns in the ciphertext that can be decrypted to maybe a word such as the. Once you know that you have a meaningful set of words, you can then use sort of reverse engineering to decrypt the rest of the message. The second technique is to exploit bad security decisions, and humans make quite a lot of bad decisions, you'll see in a second, but one of the most famous ones was the Adobe password hack a few years ago. This is where the entire Adobe password database was hacked and downloaded. As you can see, this is just a small sample of it. It was encrypted, so no problem there, except that it had so many passwords. I think it was something in the region of 4 million user passwords. Many users shared the same password. In fact, one password was used 20,000 times. What the hackers did was that they put the encrypted text into order, so they sorted it, and until they found with each password was a password hint. And while the password was encrypted, the password hint wasn't. It was in plain text. 4 million clues. As soon as the hackers managed to decipher some of these clues by combining all the password hints together, they were able to work out the word password. And once they were able to do that, because Adobe had used the same encryption key for all the passwords, they were able to decrypt the majority of the passwords using that. The last technique was social engineering, and social engineering is simply when humans are asked a series of questions by people who are pretending to be someone they're not. Basically, it's going through someone's personal records, targeting an individual, finding out as much as you can about them on social networks, to creating some sort of believable scenario for speaking to that person in real life or over the phone, get more information from that person so that you can maybe get access to a system that you previously did not have access to. Once you have access to that system, you can then go in and take more information, perhaps about that person or about another person. It's a very simple idea of just asking people for help.